Hello students, good day. I hope all of you are safe. In this module of memory management, we are discussing how logical addresses can be mapped onto the physical addresses. And under this, we saw last time how different processes are stored onto the memory. We discussed that there are a method of contiguous allocation where we have fixed partitioning and dynamic partitioning. And there are problems of internal and external fragmentation associated with them. In today's lecture, we will discuss a method of loading a process onto the memory through non-contiguous allocation. We had discussed in the previous lectures that when we want to load a process onto the main memory, we require a contiguous memory location. And this contiguous memory allocation leads towards internal or external fragmentation of memory. A wastage of memory that is either caused by some process having less space requirement than the available partition, or either it is because of small chunks of memory spread throughout the main memory, but because they are not contiguous, so they are not usable by other processes. So in today's lecture, we will discuss a method that is non-contiguous in nature. So we have this translation of logical to physical address, or we may be able to load a process onto the main memory in a non-contiguous fashion. And one process can be scattered throughout the main memory without having any sequential memory allocated to it. So this method avoids external fragmentation as well as internal fragmentation. And we do not have any varying memory partitions in paging. To achieve this, we divide the whole main memory into fixed size partitions that we call as frames. On the other side, we divide the logical memory into blocks of the same size that we call as pages. So on one side of the physical address space, we divide them into fixed size partitions, frames, and on the logical address space, we divide them into the same size chunks, we call them pages. Now we can allocate the memory in a way that when a particular process is required to be loaded onto the main memory and it has, for example, 10 pages, we allocate 10 frames that can be scattered anywhere in the main memory. We allocate those frames to that particular process, and each page is allocated to one frame. Each page is loaded onto one frame. So now our pages of a process are loaded onto the fixed size chunks, frames of the main memory. So now the operating system just has to keep track of all the free frames, and if any process requires, for instance, n number of pages, the operating system allocates n free frames to that program so that it can load onto the main memory and start its execution. However, this method requires some support from the operating system. First of all, the operating system has to keep track of all the free frames. Then it has to keep some data structure so that it can translate the logical addresses to the physical addresses. It should be able to keep track of what pages are loaded onto what frames. So all of this translation is now the responsibility of the operating system. Further, this method still has some internal fragmentation. However, we will discuss it after a while once some basic concepts are in place. Moreover, the address translation in paging is a bit different. Over here, we divide the address into two components. The first one is the page number, while the other is the page offset. Page number is the number of the page associated with the logical address space, and it provides the base address of each page that is now loaded in the main memory. On the other hand, page offset reflects the number of an instruction within that particular page, and by combining this page offset with the page number, we get the exact instruction number and where it is loaded in the main memory. Now, for instance, if we have an address space of 3 bits, which means that 8 instructions can be pointed to through these 3 bits, then for instance, if we have 2 bits in this page offset, then we will remain with 1 bit in the page number. By these 2 bits, we can address to 4 instruction per page, and for the page number with 1 bit, we can only reflect 2 page numbers or 2 pages. So we have a total of 2 pages for this particular process, and within each page we have 4 instructions, and we can use this offset to get to the actual instruction that is stored in the main memory. I hope this concept will get more clear when we will get to an actual example on the coming slides. Over here we have the architecture to support this paging process. So a logical address once generated by the CPU is divided into 2 components. The first one is the page number, while the other one is the page offset. So this page number is searched through a page table, a special data structure that contains the mapping of page number to the frame number. I give you this recall that page numbers are associated with the logical address space, where the frame numbers are associated with the physical address space. So page numbers are associated with processes, while frame numbers are associated with the actual memory locations. So over here we have a mapping of page numbers to frame numbers. This data structure, termed as the page table, is stored in the main memory against each process. So the page number that is associated with the logical address generated by the CPU gets translated from the page table into the frame number. So page number is converted or translated into the frame number through this page table, and the offset is copied as such. And now this is our physical address that we can locate onto the physical memory. Let me repeat this concept one more time. So once a logical address is generated by the CPU, it is divided into 2 components. The first one is the page number, and the second one is the page offset. Page number gets translated into a frame number through the page table, and the page offset just as such copied as at the end of this address to get the complete physical address onto the main memory. So this page number and page offset is translated into frame number and frame offset. Now over here we have a conceptual model of this logical and physical address mapping. So you can see that over here we have a process that is divided into 4 pages, and to reflect these 4 pages we use 2 bits. Over here we have a page table where these pages are mapped onto some frames, and these frames are present in the physical memory, in the main memory. So from the page table you can see that page number 0 is stored onto frame number 1. So over here at frame number 1 we have page number 0. Likewise, page number 1 is stored onto frame number 4. So we go to frame number 4 and we can find page number 1 in there. In the same manner, page number 2 is stored onto frame number 3. So at frame number 3 we have page number 2. Likewise, page number 3 is stored onto frame number 7. So we go to frame number 7 and there we can find page number 3. So you can see that in this way all of those pages are stored onto different frames that may be scattered throughout the main memory. So now we are not required to have any contiguous memory location for the storage of a process onto the main memory. So now we have some examples to deal with this concept of paging. So you can see that we had carried the very same example. Over here again we have 4 pages associated with a process, and each page contains 4 instructions. So to reflect these 4 pages we require 2 bits of memory, and within each page we require 2 bits to reflect these 4 instructions. So all in all we require 4 bits to reflect this complete process, and through these 4 bits we can reflect to a maximum of 15 logical address from 0 to 15. So now this very same process through this page table is loaded onto this main memory. So now this page table reflects that page number 0 is on frame number 5 and page number 1 is on frame number 6. Page number 2 is stored on frame number 1, while page number 3 is stored on frame number 2. Now you can see that in order to fetch any logical address that is present in this process, we have to perform that process of converting it into the page number and the page offset, and then we may be able to find it through our main memory. So let's try a couple of examples. Over here we have let's suppose instruction number 5. So its page number is 00 and 01, and within this page its offset is 00 and 01. So we are looking for 0101 as the instruction number from this logical space that we want to find from this main memory. So we know this is page number 01, so we go to page number 01 and we know that it is on frame number 6. So let's go to frame number 6. 0, 1, 0, 1, 2, 3, 4, 5 and 6. We have it in here, and the offset was 0, 1. So 0, 0 and 0, 1. We can find our desired instruction F that was in here to stored onto this location at the main memory. Let's have it with another example. Let's try to find out this instruction I. So you can see that it is stored onto 00, 01 and 10 page number. So page number 2, 10. So let's have a look at here. Through the page table we know that this page is stored onto frame number 1. So frame number 0 and then frame number 1. The offset of this instruction was 00. So on frame number 1, 00 instruction is our desired instruction. Now in terms of bits, if you want to say it, you can again get the very same result. So now let's try to translate the very same concept in here. So let's suppose if we want to translate a logical address of 0 into a physical address. So logical address 0 can be found in here. So we have 0 and instruction is A. From the page table, we get that this 0 page number is stored onto frame number 5, and instruction number or the offset number 00 will be appended or added in here. 0, 1, 2, 3, 4, 5. It is in here, and the 00 instruction is our desired instruction. And how can we translate it into the physical addresses? So we can just translate this 0 to 5, and we will get to our desired instruction on the physical memory or the main memory. So we know that each frame contains 4 instructions. So if we just multiply this number 5, the number of the frame, with 4, we get 20. So you can see that this is instruction number 20, where our desired logical address 0 is stored. Likewise, if we want to translate this logical address 3 from this logical memory and this page table and through this main memory, so this logical address 3 is in page number 0, and its offset is 00, 01, 10 and 11. So we are looking for 00 page number and 11 page offset. So again, from the page table, this 0 page number is translated into 5 frame number, and so with this 5 we get to 20 by multiplying it by 4. And now 11 will remain the same, that is 3. So we have it as this D. So 23 is our desired result. Likewise, we can do it for 4. So over here we have page number 01, and the offset is 00. For page number 1, we know it is at frame number 6. And if we just multiply this number 6, we get 24, and the offset is 00. It means that our desired instruction is at number 24 in memory location in the main memory. Likewise, you can do for other numbers. Just to have some practice, it is always good if you do this for a couple of logical addresses to grasp this concept in a clear manner. As you may have observed that the pages from the logical address space are loaded onto the frames of the physical address space, so there should not be any wastage of memory in principle. However, as we had discussed earlier, that there is somewhat internal fragmentation in paging. To understand this concept, let's consider an example. So for instance, we are working in a system where the page size is of 2048 bytes, while the process size that we encounter at any point in time is 72,766 bytes. Now if we convert this process into pages, we will get 35 complete pages, while 1086 bytes should be on the last page, that is 36th page. So this is the size of the page, and when we will load them onto the frames, these 35 pages will be loaded onto the 35 frames, so there is no wastage of memory. However, for this last page we have 1086 bytes, which means that for this 36th frame 962 bytes of memory will be wasted in this 36th frame. So this is the amount of internal fragmentation that is present in paging with respect to this particular process. And if we consider the worst case fragmentation, probably it would be like 35 pages plus only 1 byte. So the worst case fragmentation is whatever the size of the page minus 1 byte is the worst case internal fragmentation in paging. And when we take an average case, we will consider that almost half of the frame will be wasted for each process. So because there is some internal fragmentation with respect to paging, so we may want to have small frame size. However, on the other hand, if we have small frame sizes, then there may be so many entries in the page table, and it will take some time to track a particular page onto the main memory. So that is why we have to deal with this trade-off between the small frame sizes and the large frame sizes. One is better for internal fragmentation while the other is better for efficiency. Another challenge that arises when we are implementing this paging scheme is maintaining the list of free frames that are present onto the main memory. Again, for this purpose, our operating system maintains a list of all the free frames that are present onto the main memory at any given time. So for instance, if we have with the operating system, if we have a list of these free frames and we have a snapshot of the main memory like this at any point in time, and we encounter a new process that requires 4 pages to be loaded onto the main memory. So in this other diagram, you can see that this 14, 13, 18 and 20 are allocated to this process as the 4 frames so that it can load its pages onto these frames. So over here we have the page table. So page number 0 is loaded onto the first free frame, that is 14. Page number 1 is loaded onto the second free frame, that is 13. Page number 2 is loaded onto the third free frame, that is 18. And likewise, page number 3 is loaded onto the fourth free frame, that is 20th, onto this main memory. So again, this is a responsibility of the operating system to maintain a list of free frames and allocate them to a process requiring to load onto the main memory. Also, in this page table, we can add more columns to accommodate some other features associated with the execution of a process. For instance, we can have a memory protection column that suggests whether a particular page is read-only or you can write on that page or it is executable. So multiple features of a page can also be reflected in this page table. Likewise, we may add another column to the page table to reflect whether a particular entry is valid or invalid in the page table. For this purpose, we may add a valid invalid bit to every entry that is present in the page table. This page table is usually stored as a data structure, and as we have other memories which grow with the power of 2, so we have the same issue with this page table. So we may have 1 bit to reflect 2 entries, we may have 2 bits to reflect 4 entries, or we may have 3 bits to reflect 8 entries, and so on. So for instance, if we have a process that contains 5 pages, for the entries 6, 7 and 8 in the page table, we may set the bit as invalid for those particular entries. Another possible way to deal with the same issue is to use a page table length register. This can contain the value of the valid entries so that the operating system may know that all the other entries are invalid. And if we have any violation to this, we can generate a trap to the operating system. So over here we have an example to reflect this valid invalid bit in the page table. So over here we have this column that reflects whether a particular entry in the page table is valid or not. So let's suppose we have a process that contains 6 pages and we have to map it onto the main memory. So we are using a page table that contains 8 entries. So for the first 6 entries, we can just load them onto the page table, and for the other 2 entries, we can put this bit as invalid to reflect that these entries do not exist onto the main memory. Now let's consider another challenge while implementing this paging scheme. Let's suppose that you have 4 files of some text editor open onto your system, for instance Microsoft Word. So in all of these 4 files, the pages associated with the Microsoft Word will be the same. However, because the instances are different, so you may have different copies of the same Microsoft Word program loaded onto your main memory. So let's consider your file number 1. You have some pages associated with Microsoft Word, and then you have some pages associated with this particular file. Similarly, for your file 2, you may have some pages associated with Microsoft Word and then some pages associated with this particular file 2. And the very same is the case with the other 2 files. Now you can see that we have redundant copies, we have duplicate copies of the same Microsoft Word program onto your main memory associating with different files. So a solution or an optimization to this paging scheme is shared pages, where you may have a single copy of the executable onto the main memory, which is being shared by multiple files, and they can use the very same page or very same frame onto the main memory that is associated with the executable file. All these 4 files may have their own separate copies of their own data, while a shared copy of the program can be loaded once on the main memory, and that can be shared among all the instances of the same program. So over here we have an example associated with the same concept. So we have a process P1 where we have 3 pages associated with the editor, while the 4th page is associated with the data. So for this page table, we have the first page at frame number 3, second at frame number 4, and third at frame number 6, and then data is stored onto frame number 1. So you can see it from this. We have data on frame number 1, 3, 4, and 6 we have editor. Then we have this on frame number 4 we have the second editor, and then we have on frame number 6 we have the third page for the editor. Now the same is the case with the process 2, for instance, which has the first page for editor, second page, and third page, and over here in its page table we have the same entries as we have for process 1, 3, 4, 6. So over here we have 3, 4, and 6, and for its data page we have frame number 7, and you can see that frame number 7 is loaded with the data page of process 2. Likewise, for process 3 we have the first page of editor, second page, and third page, which is loaded onto the same frames as for process 1 and process 2, 3, 4, and 6. And the data page for this process P3 is loaded onto frame number 2, that is in here. So for each of these 3 processes, they may utilize their own page tables, and they may feel that their own copies of this editor is loaded onto the frames. However, we may have shared pages that are accessed by multiple programs to achieve the same goal. Alright students, so that is all for today. In today's lecture we discussed a non-contiguous memory allocation technique, that is paging, and further we discussed some issues associated with the implementation of paging. In the next lecture, we will discuss some implementation details associated with this concept. So that is all for today. Please take good care of yourselves. Thank you.